Welcome back. It's day 8. Hopefully today I have slightly better reading comprehension than yesterday. Thank you if you stuck through that whole video. Man, that was painful. Let's go. All right. So here's my starting puzzle input. Let's go ahead and throw that in here. All right. Determine whether there's enough tree cover to keep a tree house hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row. Already a quadcopter generated a map of the height of each tree. 0 is the shortest, 9 is the tallest. Tree is visible if all the other trees between it and the edge of the grid are shorter than it. We consider trees in the same row or column. That is, only look up, down, left, right. All the trees around the edge of the grid are visible. So they're already on the edge, there are no trees to block them. This example that only leaves the interior 9 trees to consider. Yep, okay. Top of the 5 is visible. Sure. It is visible here. Top of 5 is visible. Top middle 5 is visible from top and right. Sure. Not visible in any direction. 1. Sure. You can ask me to count. Total of 21 trees visible in this arrangement. 16 trees on the edge and 5 visible in the interior. So count the number of visible trees. Okay. So obviously what we want to do is we want to throw this stuff into a 2x2 matrix, 2x2 array, some kind of thing. Sure. Let's say select character int parse of the character to array to array. That gives us data that looks like we don't know. That to array. That select gives us, why doesn't it know what it gives us? Line's a string, so the select should be chars. Oh yes, it's not int parse. This is C minus 0. That to array gives us ints, that gives us int. Okay, good. So we need to count visible trees, right? So we're going to say for x is 0, x is less than, let's see, data length. All right, for int y is 0, y is less than data 0 length, y double plus. Our result starts at 0, of course. Say if x is 0 or x is equal to data length minus 1 or y is 0 or y is equal to data 0 length minus 1. Every tree on the outside is visible. So now, given an x and a y, we need to look in all 4 directions and say, do we find a tree that has a height less than us? So us is data x, y. All right, now we're going to say for int, so let's look across x. Cx is 0. Cx is less than data length. If, let's see, data Cx, y is great, is less than, let's see, less than us. Problem is if I put a continue here, it's just gonna bail out of that, right? So I'm going to put CX is data length. So we make sure to get out of here, and that means that, let's see, how about we do this? Visible is false. Let's do this. Visible is true. And then we bail out, right? And then we're going to say, if we're not visible, then we'll do this, right? And then we'll say visible is true. Actually, we can just break out of here. I don't know why I had continue. So we can just say visible. That continue goes there. And actually, that's not what we want to do anymore. We want to do this, right? And then we're going to say, if we still haven't been seen, then we're going to do this, which is cy0, cy is less than data 0 length, cy double plus. If data at x and cy is less than us, then visible is true, break. We only need to find visibility once, so if we're visible, then result double plus. And just for fun, we're going to do console write line. We're going to say x comma y is visible. Else x, y is invisible. Okay, and then we're going to return the result. So let's run this. Let's see how we do. That clearly looks very wrong. 0, 1, 2, 3, 4, 1, 1, 2, 3, 4. Right, that looks very wrong. Actually, what was the result? The result was 24. Maybe that is correct. What did it say? It said 21. All right, so if we look at this data, us at, let's do us. Let's make sure us is correct. Three zero three seven three, 30373, 30373. Okay, those are all visible. That makes sense. To make this easier for us, let's do this. We'll say our visible reason is empty string. So here, your visible reason edge. Here, your visible reason is oh, that's interesting, isn't it? That's not quite correct, is it? So white one. What are the ones that are visible? Invisible. How many trees are visible from outside the grid? How many trees are visible from outside the grid? Well, that's interesting, isn't it? It's not, this logic isn't correct. I don't need to have these reasons. I understand now. This logic isn't correct. So the visibility is really about checking everything going in both directions. All right. So what I need to find is I need to find a tree that makes us invisible, not a tree that makes us visible. Given that, I don't like this logic then. This visibility thing is not probably what I care about. I actually don't care about this. We assume we're visible. Let's see, what is the right way to do this? All right, we want to go different direction here. We want to check all 4 directions to make sure that we're looking for invisibility. Let's see, visibility, or more importantly, I think if we find ourselves visible, we can just bail out immediately. I think that's what we need to do, right? Okay, let's do that then. We don't really want this. So we want to say Cx is 0, Cx is less than x, double plus Cx. I actually think I want this still here, because this is an easy one. Right? Or y is equal to 0, or y is equal to data 0 length. Right? Then result plus plus continue. All right, so that's the edge case. So we grab us and we say, we look up, right? And we say if data Cx, y is, does this be greater? It's greater than or equal to, right? We need to make sure everything is greater than or equal to. Make sure everything is greater than or equal to. Is it everything, or we just need to find one that's greater than or equal to us? We just need to find one that's greater than or equal to us, right? Yeah, so we'll say, we'll do this. This is what we'll do then. Visible edges. Start with 0. Okay. Start with 4. So if we find anything that is greater than or equal to us, all right, then we say visible edges, double minus, and break. And then we go Cx is x plus 1, double plus Cx. Let's see, Cx is less than data length, double plus Cx. If data Cx, y is greater than or equal to us. Right, then we take this other edge away. Right, and now let's do this for y. So we do this for y, so we do cy is less than y, cy, if x, cy, cy is y plus 1, cy is less than data 0 length, double plus cy data x cy. Then if the visible edges are not equal to 0, then we do a result plus plus. All right, and here's what we'll do our console right line. Let's see. X, Y is visible. Otherwise, we'll say X, Y is invisible. So we have 1, 2, 3, 4 that are invisible, and that leaves us with 21. So 1, 3 is invisible. Let's go take a look at this. Let's go take a look at this data. So you think the answer is 21. I think the answer is 21. So 1, 3 is invisible. I agree. 2, 2 is invisible. I agree. Actually, 1, 2, 1, 2. Yeah, that. Right. Because if I look around, I see edges that hide me. Right. Okay. And now we've got 3, 1. So here we've got this is this. So that's good. And 3, 3 is invisible. So this is hidden here by the 7, here by the 5, here by the. Okay. That looks okay. I think that's all right. Let's go grab our real puzzle input, which is, of course, monstrous. Let's go see what number we get. We certainly got a lot of console right lines, because there we go, 17, 19. Let's go see how that works out for us. Okay, that's good. Let's immediately go get rid of these console right lines. There we go. Okay, what's part 2? Okay, content. Content with the amount of trees available, the aliens need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. Measure the viewing distance from a given tree. Look up, down, left, and right. Stop if you reach an edge with the first tree that is the same height or taller than the tree under consideration. The elves don't care about the distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry. So consider the 5 in the middle of the second row. Looking up, its view is not blocked. You can see one tree. Looking left, its view is blocked. You can only see one tree. Looking right, its view is not blocked. You can see 2 trees. Looking down, its view is blocked eventually. You can see 2 trees. The tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. So we're basically counting the distance until the view is hidden. So we're counting the distance until the view is hidden. Okay. So counting the distance until the view is hidden. So let's grab this, even though that's not right. It's got all the loops we want. All right, so what we want is for the result, let's see. We need to start with, so we do X and Y. Okay, so, yeah, obviously none of the trees on the edge matter because at the most they can see is 3 trees. That's never going to be enough, right? Because any tree on the interior is going to see at least 4 trees. Okay, so here we say this is us. We don't care about visible edges anymore. What we care about is distances. Let's see, trees we can see is going to be 0. So let's go up. if we find one that's greater than or equal to us, so the first thing we're going to do is every time we look at a tree, we're going to see trees we can see goes up. And when we can see one, we're done. When one is taller than or equal to us, we're done. So that's the logic. All right, so we do the same thing here, right? And then we just break. This should be this, and then this, right? And then this, and then this, and then this. All right, and then we're going to basically say if trees we can see is greater than the result, then the result is equal to the trees we can see. And then for help, we're going to say console write line, let's see, tree at xy. Tree at xy sees trees we can see, which is better. Yeah, that's good enough. And then we should return the result. Let's go back to our standard input. All right, so 1, 1, we can see 4. That's exactly what we expect. The very first thing should be at least 4. Right, and then let's go over here and look at our data, right? So we said 1, 1 saw 4, of course. 1, 2 saw 7, right? So we've got 1, 2, 3, 4, 5, 6. 6, really? 1, 2. I see 1. I see 2. I see 3, 4. I see 5, 6. Why do I see 7? What is giving us 7 there? 2, 1. 2, 1 sees 8. Sees 8. 1, 2, 3, 4, 5, 6, 7. I don't understand how I'm seeing 8. 8 is the answer, but it's the wrong answer, right? It's the wrong answer. Oh, and we're supposed to have a scenic score, of course. Right, we're supposed to have a scenic score. All right, well, let's call this the scenic score. We're going to start with 1, and then we're going to say sight distance. No, we're going to say this, right, which is the scenic score for this is going to be scenic score multiplies equal to x minus cx. We're definitely going to need some debugging here. Console write xy equals, and this is our score, right? Console write come on. Okay. So this is going to be cx minus x, cx minus x, and then this is going to be y minus cy, and then this is going to be cy minus y, minus y. And here we're going to get the whole score. Right, and we'll go ahead and do right line. Let's see what this looks like. 1, 1 is 1 times 1 equals 2. First of all, 1 times 1 is definitely not 2. Oh, yeah, this scenic score plus plus thing has got to go. But how come we're only going in 2 directions? Oh, we got to go backwards. Okay, yeah, I see that. We got to go backwards, right? Because yeah. Okay. Why is 1, 1 1 times 1? How come I don't see any other trees? I think what I have to do is this has to come out, right? So that I can use this out here like this. Right. And now we've got cy is 0. And now we don't have u, we have u, we have u. All right. And then u, and then u, and then u, and then u. Whoops, killed our break. Didn't mean to do that. 2 times 1 times 2 times 1 is 4. 4 times 2 times 5 times 1 is 40. 40 is definitely the wrong answer. Let's see if we can figure out what's going on here, though. All right, so at 1, 1, we have, let's see, we have 1, 1, 1, and 1. We should have 1, 1, 1, and 1. How do we have 2? 2. Oh, yeah, so that's the edge. So we're falling off the edge, which I guess means we don't actually care about that, which means we want to look like that instead. Okay, right? Let's go look at our input again. So, yep, that's 1, 1, 1, 1. That makes sense. We've got a 12 at 3, 4. Let's see if we can figure out why that is. What were the examples they gave us? They gave us this 5 is actually a 4. So that's 1, 2. 1, 2 is a 4, right? Because it's 1 times 2 times 1 times 2. Right? Because it's 1, 1, 2, 2. So we stopped at the 5. Okay. How about this 2, 1? That gave us 6, right? So that's 1, 1, 1, 2, 3, 1, 2. Yeah, that makes sense. That's 6. 3, 2 is the 8. That's this one, right? So 1, 2, 3, 1, 2. This is the 8. All right, so we've got 1, 2, 1, 2, 1, 2, 1. So that's 8. So where did we get this 12 from? 3, 4. This is 1, 2, 3, 1, 1, 1. 2, 3, 1, 1, 3, 4. What did we do wrong here? So we think we got 3 in this direction. 1, 2, 3, that's correct. We got 1 in this direction, that's correct. We think we got 1, 2, 3 in that direction? That doesn't seem right. 4, we can't get 4 in any direction for this. How did we get 4? How did we get 4? That doesn't make sense. What have we done wrong? Okay. So we go from x minus 1 to 0. We go from x plus 1 to the edge, right? We have, let's see, let's do us up here so that we can do us and make sure that we are seeing the correct tree. So this is the 9 at 3, 4. The 9 at 3, 4. Is that really what's at 3, 4? 1, 2, 3, 1, 2, 3, 4. Oh, we shouldn't be going over. We shouldn't be going there. Ah, -1. When I rewrote that, I missed that part. So that's our 8. Okay. That looks okay then. Let's try the real data. See where that gets us with all the ding-dang console write lines. 590,824, 590,824, 590,824. Okay, looks good. All right, not too bad today. I think that turned out okay. I mean, there's obviously a lot of edge cases in these things. It's pretty common in Advent of Code to have these grids of things where you have to have special handling on the edges. Like that's actually really normal in computer science in general when you have grids of things to they're literally edge cases when you're on the edge, right? And so making sure that you're handling all the edge cases correctly is certainly an important part of that. As you saw, like all the problems I had were making sure that I really understood the algorithm, because in both cases I thought I understood the algorithm until I actually started thinking about it and then didn't. But B, making sure that we hit all the edge cases correctly. Like for example, stopping at the edge instead of beyond the edge, and then also not including any of the edges. Both of those were really important today. So, well, there we go. That's day 8 in the bag, and I guess we'll see you tomorrow.